Hello, one and all. Can you hear me okay, even without the getting close up to the microphone? No, I'm saying, no, John, you need to be louder. Okay, let's see what I can do. How's that? Is that pretty good? Everyone feels comfortable? Okay, then we'll try to stay there. First, welcome, and thank you for joining today's panel discussion, Reining in Global Warming. I am Dr. Dawn Cardace with the University of Rhode Island's Department of Geosciences, and personally and professionally interested in climate change. I'm proud to stand alongside four wise commentators here today. Dr. Marion Gold of the University of Rhode Island's Energy Center, Dr. Jason Greer of the Environmental Protection Agency's Atlantic Ecology Division, Dr. Pat Logan of the University of Rhode Island's Department of Communications, and Dr. Becky Robinson of the University of Rhode Island's Graduate School of Oceanography. And I'm proud to be in the company of so many interested, concerned people. I'd like to share with you right now, just in opening, a few comments on material from the Copenhagen diagnosis, essentially a summary of the physical sciences basis for the publications of the Intergovernmental Panel on Climate Change, co-authored by 26 leading climate scientists. Sorry, somehow I got on the wrong podium. Is this still okay on the camera? Okay. John, we're having a tension about that. If we want it to look good for everybody who's watching this streaming live, we need more light. So if you can possibly bear it.
It's hard on us.
It's hard on us too.
Right.
So according to the Copenhagen diagnosis, co-authored publication, about 26 leading climate scientists teamed up and wrote this update to the last IPCC report. These are their comments. On surging greenhouse gas emissions, global carbon dioxide emissions from fossil fuels in 2008 were 40% higher than those in 1990. Even if global emission rates are stabilized at present-day levels, just 20 more years of emissions would give a 25% probability that warming exceeds 2 degrees C, even with zero emissions after the year 2030. Every year of delayed action increases the chances of exceeding that 2 degree C warming. On recent global temperatures demonstrating human-induced warming, over the past 25 years, temperatures have increased at a rate of about 1/5 of a degree Celsius each decade, in very good agreement with predictions based on greenhouse gas increases. Even over the past 10 years, despite a decrease in solar forcing, the trend continues to be one of warming. So natural short-term fluctuations are occurring as usual, but there have been no significant changes in the underlying warming trend. One more bit to read to you. On underestimated current sea level rise, satellites show recent global average sea level rise at about 3.4 millimeters per year over the past 15 years to be 80% over what we predicted in the last IPCC report. This acceleration in sea level rise is consistent with a doubling in contribution from the melting of glaciers, ice caps, and the Greenland and West Antarctic ice sheets. So what? I say that so what is we need to stand up and take some action. And that's why I hope that we get some real discussion going with this panel of experts here today, helping us draw lines in the sand, so to speak. So with that, I'd actually invite Dr. Marion Gold to lead us with her opening few comments. Oh, sorry. Sorry, Marion. I did resize a figure that I thought of general interest, so I'll slide this in right now. This is a really nice image. You should recognize the shoreline of Rhode Island somewhere in there. Yeah, this is an estimated sea level rise and its impact on the immediate locale. Okay, and I'm happy to post this.
This is Route 1.
Oh, thanks, Pat. Yeah, this is Route 1. If you can find it amidst the green and blue. But this is easily accessed online, and if anybody of interest would like a copy, I can share it with you. Just contact me by email at the conclusion of the talk. Yep. Okay.
All right, thanks very much, Dawn. My name is Dawn, as said, it's Marion Gold, and I'm the director of the URI Outreach Center and also the Energy Center. And I am probably the most practically oriented of the speakers here today. My mission at the Outreach Center is to take university-based science information and bring it to Rhode Island residents, businesses, community decision makers so that they can use that to provide local solutions to some of these global challenges. Let's see, enter, is that right? Down arrow, okay. As I said, I'm the director of the URI Energy Center. This is part of the land grant mission of the university. This is the branch of the university that, as I said, extends knowledge to the local community. We have three main program areas: sustainable agriculture, sustainable horticulture, and our most recent initiative is sustainable energy. Did it click? We are in the fourth year of an Energy Fellows program, and this is a program that takes students from a variety of different academic backgrounds, and I think we have some here today: engineers, economists, geologists, political scientists, and we put them to work on a funded opportunity to address a real-time energy challenge ongoing in the state, so that they get a chance to put their academic skills to work, and they work in interdisciplinary teams, so it's been a terrific program. We also do educational programs for the general public, and that's why I said I'd like to have that slide. One of the programs we do is the Master Energy Program, and I think today we're going to hear about some of the technicalities involved with global warming, and I'll get to the connection between global warming and energy in a second, but it's often so technical. 99% of the people out there in Rhode Island don't have a clue what we're talking about, and I think with climate change, the danger is people often feel hit over the head with an insurmountable problem that they can't do anything about. So by bringing information about the energy situation to them and about concrete steps that they can take in their home or businesses, it gives people a sense of control and actually, I think, can contribute to some of the solutions to the problems. We do a lot of general public events as well. This was an energy expo that we held in 2008. We had 6,000 people at the Reining Center who were all eager to learn about energy. Now, why am I talking about energy? This is a really useful graphic. It shows the relationship between energy and greenhouse gas emissions, and as you can see, as much as 75% of greenhouse gas emissions can be traced back to energy production. And this graphic is from a terrific book called Sustainable Energy Without the Hot Air by David McKay. He's a physicist in Cambridge. Shortly after he wrote this book, he was appointed as the chief scientific advisor for Britain's Climate and Science Advisory Panel. So a terrific book. It's available free online. The bad news on the energy front is that, as you probably know, we get 85 to 90% of our energy currently from fossil fuels, and this is a really sticky problem. Despite a lot of pretty good direction coming from the federal government, or at least from the president, like the announcements that were made yesterday, we still are relying heavily on fossil fuels. As I was driving here, I heard a really interesting thing saying that National Grid had just lowered its household electricity rate by 26%, I think, because of the inexpensive natural gas coming into the system. So there's pros and cons on that. In general, fossil fuels are dirty, even though they're cheap, because we can't seem to get around to factoring in the externalities into the price. And also we have well-entrenched economic interests on the side of fossil fuels, whether it's the large oil companies that are headquartered in the United States or the even more entrenched state-subsidized oil regimes like in Russia and the Middle East. So lots of challenges. The good news is we are working towards a sustainable energy future. Rhode Island has one of the best energy efficiency programs in the country, believe it or not. We've set a very ambitious goal of reducing our energy use by 30% over the next decade. We've also committed to 15% of our energy coming from offshore wind farm, and then we're slowly trying to make progress on smaller scale distributed energy generation. I was at a meeting of the Renewable Energy Task Force, which is a group of small business people who are working, trying to figure out how can we do better on renewable energy, offshore wind farms aside, and we're not very organized in that regard yet, but we're making some progress. So that's the good news. Energy efficiency in particular is fabulous. It's one of those rare win-win opportunities where it works for the consumer because our rates go down as we decrease our usage. It also works for businesses. spurs job creation. We're putting $45 million into energy efficiency this year alone. That's going to spur all kinds of job opportunities for small businesses. I'm almost done. And again, as I said, the good news is when you invest, it only takes 4 cents to invest in a kilowatt hour of energy efficiency versus 13 cents per kilowatt hour on fossil fuel. So that's a good thing. Renewable energy is a little more challenging. It's more costly, but we're working on it. And so my final word, this is somebody else's slide. It's a cartoon. The bottom line is whether or not you buy into the climate change, and I think obviously everyone in this room is very, very concerned about the ramifications of climate change. If we work towards a clean energy system, we can address 74% of the greenhouse gases that are related to energy production and get all these other benefits at the same time. So look forward to the discussion. Oh, and I just want to say it's a great opportunity. There's lots of opportunities out there for folks like you who are getting trained right now, because this is a challenge that is not going to go away in the next year or two. So we're looking forward to having all your engineers, economists, geologists, and political scientists and communication people out there coming up with solutions. So thank you.
Hi, I'm Jason Greer. I'm from the Environmental Protection Agency, which has a laboratory over on the Oceanography campus. I'm an ecologist there. How do I get to the next slide? Okay, so I want to start by showing you a famous time series of CO2 measurements from Hawaii. The dark band, the longest dark band there, starting in, 1960 there, it shows the concentration of atmospheric CO2 at that monitoring station. And this is one of the most convincing pieces of evidence that you can show to just to document that the concentration of CO2 in the atmosphere has changed. Rebecca will be talking about another kind of evidence later on. So the other line that you can see there, the second one down, is the concentration of carbon dioxide in a nearby ocean station. So as that atmospheric concentration goes up, it equilibrates with what's in the ocean. And then that bottom line, the one going down, is seawater pH, or the acidity of pH at that ocean monitoring station. So what's going on is that this CO2 is interacting with the ocean. Somewhere around a quarter of that CO2 is ending up in the ocean. And at EPA, one of the areas that we're most concerned with in a variety of our programs is the coastal environment and how things like ocean acidification might affect that coastal environment. So what's happening in the coastal environment is, you can see up here showing the riverine inputs. So there's carbon and CO2 that makes it into the coastal environment from rivers. There's also carbon that comes in atmospherically. And then there's also all the respiration processes of the biota in that coastal environment, adding CO2 to the seawater. So what's going on here is that it basically has to do with the carbonate chemistry in the ocean. The CO2 that ionizes into a couple of different ionic forms, leaving this acidic condition that makes it difficult for shell-building organisms to build their shells. And this isn't just things like clams and corals. There are also planktonic organisms that form a very important part of global carbon cycles and calcium cycles that are also impaired by this acidity. And there are a lot of other physiological processes that are affected by the acidity of the ocean. So in all of this that I've told you so far, this is just the trail of breadcrumbs that sort of connects the small world that I work in to this bigger issue of carbon emissions. I focus on the effects of this acidification process on marine organisms. And all I'm trying to show you here, I don't want you to worry about the text at the bottom. That's just to give credit for the sources of the images. But the point here is one of the things that's coming out of the science on this issue is that every different kind of organism has a different kind of response to acidification. In fact, there are some organisms that do better under a CO2 enriched environment. And that makes this task of predicting what the effect of ocean acidification is going to be very difficult. It actually even makes the job of understanding the biogeochemistry of the carbon cycle very different. So, so what I do is I look at different kinds of animals. I develop methods that allow us to relate the studies of the organismal level biology to what we think might happen to populations in the wild. So the way a lot of science is done, whether it be toxicology or ocean acidification, is that we study things like the effect of environmental stressors on, say, reproduction or on survival. But if you study those things in a beaker in the lab, that's not really necessarily going to be predictive of what's going to happen in the field environment, especially when you have things like competition and interaction between species and things like that going on. So my world is sort of the mathematical models and the testing of those models in the laboratory that allow us to understand the ecological relevance of this kind of process.
Welcome, Dr. Pat Logan.
This is the second time in over 34 years that I've been invited to say something in public. Hope it's not the last time. Last time I shared a stage with the director of Sea Grant program. We had an hour to talk about our programs. An hour and 10 minutes into the program, he turned to me and said, "Is there something you'd like to say?" So I appreciate Don's taser moving things along here. Good. Is it, yeah, do this thing. Okay. I chose one slide because I have trouble with buttons and can't change them, but this slide represents basically the period of my career. Limits to Growth was written in 1972 when I was an early graduate student at Michigan State, a student in entomology. No, I didn't spend my time pinning bugs. I mainly spent my time learning about nonlinear system dynamics and non-orthogonal problems and computer simulation, so I understood what these people were saying. I also spent a lot of time in the field counting insects and making sense of them. That's what science does. It observes, and from what it sees, it reasons. And occasionally it reverses that process. It develops models and reason, and then seeks to observe, to confirm, or change the reasoning. Science does a good job, the natural sciences in particular, of making us aware. We know a tremendous amount about climate change, about petrogeology, about limited resources, about our ability to feed and water ourselves in the future. Science is doing its job. Al Gore, when he wrote Inconvenient Truth, was asked, why did you put all that yuppie stuff at the end? The solution is going to be to buy green products, get a Prius, change your light bulbs, and not the really big issues, not the really important things of changing collective human behavior. Why did you do that? He said, because you can't act until you're aware. Now, science is trying to make us aware, but we're not acting. We elected a group of representatives and senators this year that take the ideologic perspective of there is no climate change, there is no global warming, it's a hoax. And we'll see the specter of Issa and Sensenbrenner and Inhofe investigating ClimateGate for the 8th time this year and trying to expose the hoax. The consensus of science makes us aware, but we don't act on it. My concern these days is why not? What's broken between the science discourse communities and the public sphere? I'll suggest, and it's important because from what we're aware of, we need to behave. It needs to get into the regulatory sciences. It needs to get into economics and education, to the judiciary, to political science, and even into religion to change human behavior. Let me just outline 3 or 4 points that I think are really the heart of the matter. As science continues to do its job, the social sciences need to do a better job. Number one, science doesn't talk to us. It does science speak and it talks to itself. It demeans efforts to get out of the academy and speak to the public. It does a poor job of that, and the culture and the mechanisms for speaking about the things that matter needs to change within the science discourse community. We need to reward engagement, particularly in the public universities. We need to do a better job of handling, okay, I got 1 minute here, so I'll finish this up. We need to do a better job of handling the complex. We need to do a better job of handling the uncertain. We need to create a population that is less naive and that is less optimistic, because optimistic is not realistic these days. And I'd be glad to come back to those, but I did finish under time.
Hi there. I had to return this to its low height. I'm Becky Robinson. I'm from the Graduate School of Oceanography down on the Bay campus, and I teach an honors climate change in Kingston every fall. A climate change course, every fall. And I'm a geologist, so I look at climate change from a pretty different perspective than sort of Jason's change in CO2 every year. I think about it on longer timescales and sort of natural variability, but I also I try to use what we know about Earth history and about the geologic changes in climate to help us understand what's going to happen in the future. So there have been lots of sort of little mini experiments conducted by Earth systems that can tell us how carbon goes from the atmosphere to the ocean and into the land and back again. And so those big cycles sort of on the global scale are really what interests me. So Jason promised that I would give you guys a different view of atmospheric CO2 and how we know it's changed. So this is glacial interglacial scale climate change. So we had the last peak of the last ice age was about 20,000 years ago. That's here in this green line. And it was a period of cold, Rhode Island, a lot of the lakes and swamps and those were under ice. Cape Cod is a moraine. That's an end moraine of glaciers, right? So this is where that, maybe this is the LGM. John can tell us for certain. So this is atmospheric CO2. This is something called delta deuterium. Deuterium is just heavy hydrogen. It's a proxy for surface air temperature. It happens to be surface air temperature on Antarctica because this is an Antarctic ice core. But it tells us that air temperature was cold the last time atmospheric CO2 was very low, and ice was almost everywhere in the high latitudes. And then I also have insoluble dust, and I'll get to that in a second. And so this is 400,000 years. And so we have sort of a rhythmic pattern. 100,000 years, we get an ice age, then we come out of it, and we get an ice age. And so some of the climate skeptics like to use this as an example of natural variability of climate change and how climate is going to change. It is always changing, and therefore this sort of current change in CO2 is not a problem. How many people saw The Inconvenient Truth? Okay, so do you remember this plot at all? Any of you? So do you remember at the very end, sort of at the very top, Al Gore got on that stand that goes up and up and up and up and up, and he tried to show where current atmospheric CO2 would sit on this plot. So this is 100,000 years. So maybe from 0 to, we would have to just go straight up to, what's the atmospheric CO2 concentration today? 392, thank you. I was going to say 390, but I round down. So now go up 100 ppm. So this is a glacial interglacial CO2 change of about 100 ppm, but it's happening virtually in 1 pixel on this graph. So the rate of change of CO2 right now is so much faster than anything that we have experienced in sort of recent for me, I'm a geologist, climate change. We're redlining it to sort of the Eocene, which was 35 million years ago. Okay? That we're really changing the Earth system. But we're not the first organisms to change the atmospheric chemistry of the Earth, right? We got oxygen 3.2 billion years ago, right? So photosynthesis changed the chemistry of the Earth, and so I guess we can follow our own experiment. Okay, so I promised I would get back to dust. So why does it matter? It's cold, got big glaciers, atmospheric CO2 is low. So why would I put dust up here? Why would anyone care about that? So one of the things that a geochemist or a paleo person, someone that looks in the past, can sort of try to inform the current climate change debate is about the role of things like micronutrients. And so carbon goes into the ocean in various ways from the atmosphere down into the deep ocean. But one of those ways is by what's called the biological pump. So nutrients come into the ocean. If they're in the surface ocean in the presence of sunlight, plants take them up and they make biomass. They make organic matter, which is carbon-based, right? That organic matter sinks out. If it makes it into the deep ocean, it's stored for maybe 1,000 years. Okay? So we can start to ask questions about if we change sort of the total quantity of nutrients in the ocean. In this case, I have nitrate and phosphate, but iron, which comes from dust, is also a nutrient. If we change that total quantity of nutrients in the ocean, could we change how much carbon plants can take out of the surface ocean and put in the deep ocean? And so one of the engineering solutions to global warming or to atmospheric CO2 problem is to put a lot of iron in the ocean and try to fertilize the phytoplankton so that they'll sequester more carbon in the deep ocean. It's not a realistic thing to do, and that's one of the things that the geochemists and oceanographers who study sort of the climate system on longer timescales can guarantee. It's hard to get iron in the right places, and it's not going to happen on a timescale that's fast enough. The ocean will make sure, because of its sort of slow 1,000-year overturning rate, that putting a little bit of iron in the ocean is not going to sequester enough atmospheric CO2 to change the system. So that's just one example of how sort of looking in the past could help us to try to understand the current dilemma. Is there anybody after me?
Now we're going to pull our chairs a little closer. I will prevent anybody from punching anybody else up here. And I'm going to ask those of you in the audience, if you have questions that you'd like to bring to this group of people. We have 2 graduate students who will be sort of pacing the margins. Just go ahead and put your question on a piece of paper and hand it out to one of the aisles, and we'll try to take those. I'm going to start though with questions submitted by you and your fellows to the professors of a few classes involved in advance. So we'll start there and see how far we go. So one of the first questions that we received here when we requested a pile from students involved in courses related to global warming and climate issues was thinking about environmental policy. So under policy, why was there a standstill at the Copenhagen meetings? Why has there been so much stress related to the Kyoto Protocol, to sign or not to sign? What are the common issues around the United States as a country not supporting these initiatives? Let's see what we make of it.
I'm not an expert on these intergovernmental or international conferences. Kyoto and Copenhagen, remember, are not just gatherings of scientists. They're government representatives and industry people as well. It's a little different from scientific peer review because these others are invited in. It's quite open, and it's often a bit political. We slowed down because the science that we understand suggests we need some fairly large changes. Those changes are expensive, and those who would have to spend the money don't want to spend it. Nicholas Stern in the Stern Commission report suggested that, look, if you don't do anything, you'll lose a significant part of your gross domestic product. It will cost you. Climate change will cost you. Sea level rise, flooding, crop problems, it will cost you. How much? We don't know. It's not that precise. Maybe 5 to 20% of GDP, he said. Now, this is a conservative organization. This is the Chancellor of the Exchequer in England. I think that's about as conservative as you get. He said it might cost you 1% or so of GDP to act, to head off problems. We don't want to invest that 1%. Henry Waxman last week said that in Congress, we don't listen to scientists and experts. The voices that matter are the voices of Koch Industries. How many of you know Koch Industries? Koch Industries, David and Charles are the third richest people in the country right now and investing a tremendous amount of money to fight the hoax, to keep from having to respond to regulations for climate change. Why? Because they own pipelines and industries. They would rather not deal with the expenses. I think when those factors are allowed into the arena, the science gets mixed with the politics and we stop. We may be stopped for quite a while, but that's something we need to focus on, which is why I get hung up. It's not such a matter of science per se. It's the ability of deniers and contrarians for ideologic or greed purposes to steer the conversation and to slow it up. That's a horse I'll get on anytime, Ryan.
Yeah, no, I think you're right.
I have a hunch we'll be hearing a little bit more on that tone as we continue. This was actually a question submitted for Rebecca. But I actually think also anybody with any mind to speak should. And you may have something to say on this, Marion. Just specifically details, thoughts about a possible reasonable cap and trade policy for CO2 emissions in the U.S. and perhaps regionally, sort of first principles and maybe best practices.
So can you repeat the thoughts on
Cap and trade and CO2 emissions mitigation. What do you think of it?
what do I think about cap and trade? Cap and trade worked for. Ooh, is this not on?
Yeah.
It worked for sulfur pollution and for sulfate sulfuric acid deposition problems in the U.S. And so let me stop first. Does everybody know what cap and you covered cap and trade?
How many people are happy hearing about cap and trade, a quick definition, or you know what it means? You know what it means? Raise your hand. We've got a lot of yeses. To my mind, it's an economic policy that basically sets a target limit for total carbon allowable. And then you kind of let economics do the rest. So to bring all the different contributors, thank you. To bring all the different contributors into play. Oh, thanks.
Can I I'll just say, we have a very effective cap and trade program in New England, the regional greenhouse gas emissions control. It's kind of a model for the country, and we had been thinking that, what's going to happen when it goes nationwide, but that doesn't seem to be happening. But it's provided a really wonderful pool of resources that can be put into programs like energy efficiency and renewable energy. So it seems to be working really well. It's not perfect, but.
I guess I was just after I made sure everyone knew what cap and trade was. Sorry, I was going through my teacher.
Smart.
That was the only thing I was going to say was we have a regional program. I think there's a lot of reluctance on the part of policymakers to engage in anything related to sort of either cap and trade or a carbon tax or anything. They're just, I think it's very political, right, and costly, but it could work. It worked for sulfate. It was much more tractable with sulfur. I don't know. I don't know if I have anything.
Just add one thing that kind of goes along with what Pat said. I have some friends who work on this issue nationally and internationally, and they say in the United States, until we do campaign finance reform, we're not going to make any progress because there's so much vested, so much money from the Koch brothers and others going into it. So it is really political. And you wonder how many disasters we have to have before, someone gets hit over the head and makes a change. But we will focus on the positive if we can.
Did you want to say a word?
Yeah.
These are live.
Oh, yeah.
This is just extra.
I was just going to say something that's not specifically about cap and trade, but a related concept in clean water policy, which is something called total maximum daily load. The way the Clean Water Acts, parts of the Clean Water Act work, is that bodies of water, places like Narragansett Bay, Puget Sound, or whatever, are evaluated and determined as to whether or not they are impaired by a particular environmental stressor like nutrients or chemical contaminants or whatever. And then if they are listed as impaired, there has to be a plan, or a plan is eventually developed where that defines a limit on how much loading there can be to that system. And in the case of CO2 effects on those water bodies and ocean acidification, which is actually an issue in the nearshore environment, the tricky part of it is that greenhouse gas emissions are subject to regulation under the Clean Air Act, but this policy about total maximum daily loads is under the Clean Water Act. And so it creates sort of there are some institutional complications there that make it difficult because the regulatory policy would mostly be under the Clean Air Act.
So I knew what I just remembered what I was saying when I started talking about the sulfate. So, but the cap and trade for sulfur, part of the reason that it worked was we could see the results. We knew where the sulfur pollution was coming from, and we could measure the change in deposition. But CO2 is a global problem, and so regional cap and trade efforts are not necessarily there's no sort of positive reinforcement or motivation for keeping them in place, if that makes sense. It's very hard if we have a cap and trade in the U.S., how are we going to actually see any positive results if, say, everyone in India has one of those little $1,000 Tata cars? It's this is a global problem.
Going right from that into the next question that was submitted actually online said, kind of all of this considered, even if society were to go green, curb carbon emissions to a fraction of modern levels, how long do we really think it would take for the environment to turn around? And what are your thoughts on that?
Yeah. So there are numbers. There was a recent maybe Science or Nature paper that did the math in a global climate model, and they said, okay, if we go to 1990 levels, so Kyoto, how long will it take before we can see a change? And it's 200 years, it's centuries. It's already built into the system. If we stop polluting today, it's going to take way more than your lifetime and your children's lifetime to actually see any positive change.
Think of it this way. Think of it as a filled bathtub with a little tiny bit leaking out the drain. And the faucet's turned on full blast, and it's filling up, and it's going to overflow. Well, okay, turn down the faucets, a whole bunch. It takes a long time for the carbon to come out of the atmosphere. It's in terms of hundreds of years. And the figures I think we saw last year was if we continue loading, it'll take past 3,000 to come down. Okay. So you need to stop loading it. That takes a tremendous cut in the amount of carbon. And Jim Hansen says, look, realistically.
Oh, who's Jim Hansen again?
Who knows Jim Hansen? Well, that's one of our disconnects. And Jim Hansen is the director of the Goddard Institute for Space Studies and one of the most outspoken climate scientists. Storms of My Grandchildren, 2009, James Hansen. A good read if you're a little nerdy, because it's kind of, he loves to be a professor and talk science.
I'm reading it right now.
Yeah, well, I read it too, and so have some of my friends, so we'll. Now, the point is, Jim says, look, best of observations and modeling, best current reasoning says you dare not put the carbon from the coal, all that carbon, into the atmosphere. Realistically, we'll burn down the oil. We'll burn off most of the natural gas. All of that goes up as CO2. We can't change it that fast. But dang, folks, stop putting the coal. Don't plan on putting the coal in the atmosphere. Leave it in the ground. Now, this is a world where China's putting up a new coal plant once a week, where our economy is turning to clean coal, which doesn't exist yet, as an agent of the economy. So we're pitting disciplines. We're pitting natural sciences against economics. And let me harp 1 second. The problem with that is we're not attuned in that regulatory mechanism of higher education to deal with the complexity or the interdisciplinary nature of the problem. The economists do not listen to the natural scientists well enough. The political sciences don't. We are set up for the 1800s, the 1900s, but not for this century, because we're not talking between the sciences that define the problem and the regulatory sciences that act on the problem. Carbon trading, great, but why do you give somebody a license to keep doing what they're doing just because they have enough money to buy some rainforest acreage? They're still putting stuff up in the atmosphere. You've got to set a cap, you've got to get under that cap, and that's going to be darn hard.
So I think we are talking, but I'm not sure we're talking to the right people. That's one thing. And I know that in China, I mean, they're up against it. Their environmental problems are so much worse than ours. They're much closer to the edge. And it's really interesting, though, because they are a state-controlled system. They can go and say, we want, 10 wind turbines there now. And they have a lot more control over their system, which we don't seem to be able to take that step to push people that way in the United States. So, but maybe we'll get there with a few more disasters.
Oh, this is dangerous.
Here, let me just give that to you.
I'm going to take one more question out of the prior submitted ones, and then I'll encourage the grad students to kind of run down this side and hand me any other questions that are surfacing from the community here. But mindful that we have some CO2-minded scientists here, there was actually a pair of questions. One, quite literally, given the CO2 in the atmosphere, how much goes into the ocean anyway? Any kind of rules of thumb about that? And then, let's see, it was a direct call then for ocean acidification and any kind of immediate suggestions on our part for ways to combat that, even regionally. So that's kind of 2 questions. Do you want to think about CO2 loading in the oceans first, and then mitigation strategies?
The number that is usually thrown around in terms of how much CO2 is absorbed by the oceans is that somewhere around 1/4 to 30% of carbon that's been put into the atmosphere since pre-industrial times is going into the ocean, has gone into the ocean.
Yeah, so you put CO2 comes out of your tailpipe or out of your coal plant, and it goes into the atmosphere, and then about 50% of it is missing from the atmosphere. So we know about how much fossil fuels we've burned, and we know what atmospheric CO2 concentration is. And there's a difference of about 50%. And of that 50% that's missing, we have 2 places it could go. It could go to the ocean, or it could go to the terrestrial biosphere, so to trees and plants and soil. And it turns out that CO2 is a little bit of a fertilizer. So if you put CO2 in the atmosphere, some plants will grow faster and they will take up a lot of that carbon. So about 50% of that CO2, 50% of that 50%, more or less, so 1/4 goes into the biosphere, and the other 1/4, sort of by subtraction, we think goes into the ocean. That's been confirmed because when you put CO2 into we can now measure that by looking at changes in oxygen in the ocean and sort of doing a back calculation for how much carbon must have entered. So it's a game of budgets. And then
Any suggestions about what to do about ocean acidification in the near term?
I mean, it's a global problem, right? So, the atmospheric concentration of carbon dioxide is what it is, but I think Jason might be able to speak to sort of exacerbating things like nutrient loading and things that make the pH problem worse.
So there is a lot of analysis of what's referred to as policy adaptation. So if you think about, all right, what if we were to say, okay, nothing's going to be done about CO2? Are there other things we can do to reduce the impacts of CO2? So an example is that the pH of seawater affects the toxicity of metals to organisms. So perhaps regulatory policy concerning metals needs to adapt to the possibility that there's going to be this exacerbating effect. So that's one example, but that's a huge aspect of the problem. So instead of kind of sitting back and saying, well, there's nothing we can do, regardless of whether or not CO2 is brought under control, there are still adaptations in policy that are being looked at.
You TAs just have to come run up and, hand me any questions that come out from the group. But I'd like to telescope back out a little bit. This question was a little bit wider, a lot wider. Just said, really to you, what is the most critical link between global warming and energy? We could probably all answer that differently. Links between global warming and energy patterns.
75%?
Sorry. See what you mean.
So, I mean, global warming and energy production, as I said, are it's like the big elephant in the room. So if we can develop clean energy systems, we'll have made a bit of progress to reducing greenhouse gas.
I was taking that question as being more sort of philosophical or subtle or whatever. I would just point out that a lot of science going on right now, at least in sort of the federal response to these problems, and also in outside of government, has to do with what you've probably heard of referred to as ecosystem services. And there's an attempt to incorporate social sciences formally and rigorously into decision making. There are a lot of questions that brings up about whether or not the services that we get from ecosystems can be monetized, but that is one of the ways that this question of the cost of producing energy versus the economic value of that energy people are trying to look at those questions by merging social science and natural science.
Since that was such a better answer than what I gave, and that would make it easier for the decision makers to make a decision to institute a cleaner energy. Okay, thank you.
Then I have a pair of questions here. The first, we'll start at the top. If the trend change in terms of CO2 in the atmosphere and its impacts will take hundreds of years, are we looking at agricultural crashes in the mid-latitudes and water shortages?
Yeah, we are.
I agree.
Powell, Deadpool, the Southwest, running out of water. I forget her name.
Elizabeth Colbert?
No, Colbert, yeah. A number of authors have suggested we will have trouble with climate change. Climate change means, hey, it rains too much, it has too much drought. That affects crops. That affects the amount of standing water. Sea level rise affects salt intrusion in coastal areas. It's a big darn deal. Serious questions about how you feed and water an increasing population. Those are the artifacts, those are the vulnerabilities that result from unconstrained climate change. No question. That's a focal area for the IPCC. It's not just the basic science, it's also what does that mean for vulnerabilities, and the third area is how do we adapt to it? Do we just live with it and get in our boats because the seas are rising? How do we respond to it? But unquestioningly, this will affect our ability to feed ourselves. It's already doing it. Look at the droughts and the grain supplies around the world. Why did we have a riot in Tunisia? It wasn't because of a newfound love for democracy. It's because food prices got too darn high. People couldn't stand it anymore. That happened in 2008. That's climate change coming home.
Next is the buffering effect of the oceans with respect to CO2 uptake, preventing temperatures then from increasing at an even higher, faster rate? And if so, when will the buffering effect be exceeded?
I can't remember when the buffering effect will be exceeded, but as you put more CO2 into the ocean, the capacity of the ocean to take up CO2 becomes less. And so we get sort of, so as relatively pristine, untainted water comes to the surface by a process called upwelling. It brings water from the subsurface up to the surface. That water is more able to, it's like a sponge, it's more able to take up CO2 than other water. But eventually, sort of in the overturning time of the ocean, we're going to get closer to saturation, and we're not going to be able to take up. So that ability, so that 25% will become 20%, will become less and less. And I can't remember what the outlook is for how long that takes. But it already appears to have slowed down to some extent. And you might know the numbers. Was that?
I don't know the exact numbers, but maybe what we'll do is update with a little web posting on the URI Geosciences webpage under my name, and I'll put a little bit of a sort of press release banner following today's talk. And a few of these unresolved quantitative questions we'll try to nail for you there. But actually, the two different people asked very related questions just now. The first says, is it realistic to rely on technology to correct the warning? And then the next person wrote, could we actually increase absorption of CO2 in the Earth system somehow, technology, instead of just reducing our CO2 emissions? So that's a pair of related and strong questions.
Yeah, so we can't just scrub CO2 out of the sort of ambient air very easily, right? We have ways to capture CO2 chemically, but then how do you transport it and store it? These are sort of big issues. And so some of the ways that we can try to remove CO2, we can do it at the tailpipe or at the smokestack, and it's coal capture and storage. This is clean coal to some degree. So there are ways that we've thought about engineering our way out of this system to be able to sort of burn fossil fuels freely and then still not sort of feel the pain. But we need to lower CO2, and so I sort of hinted at this idea that we could maybe fertilize the ocean and take CO2 out that way. It doesn't work it won't work, not on timescales that we're interested in. But there are lots of ideas for cooling the planet. How many of you have heard about the idea that we could put space mirrors up into the atmosphere? So this wouldn't do anything for pH or the changes in atmospheric CO2, but it would help cool the planet. It would increase our albedo, how reflective the Earth system is, so that the total amount of incoming solar energy would be decreased. So that's sort of one really sort of kooky idea.
I'm gonna give Pat an opener here to expound ad nauseum on this question. This relationship between technology. I see a connection between technology and behavior. I'm not an expert in this thing. This is more of a personal reflection. But if I trade in my pickup truck for a Prius, will I just drive more, or will that become, a way for me to reduce my carbon footprint? So do we see technology as a way to maintain growth or a way to cut back on carbon?
I'm working on a paper on varieties of faith in a century of limits, and we have faith in many things, not just a religious kind of faith, but faith in technology. The space mirror will save us. We have faith in free markets. Things will be more expensive and we'll find another way of doing it. We'll make electric cars. We'll find a substitute for the fossil fuels, which will run out in mid-century, pretty much. But by that time, most of the carbon from the fossil fuels will be in the atmosphere, and it's going to stay there for a long time. I'll just respond this way. The techno fix is what we do when we need an answer and we need optimism. It's not necessarily realistic. It's not necessarily the best answer. Face it, we have too many people on a finite surface, we consume too many products, and we emit too many residuals from our settlements and industries. Parts of the world are reducing their population. Italy, on its current trajectory, will go from 56 million to 8 million by the end of the century because they don't have kids anymore. Change the stupid diapers. Germany's doing the same thing. Not all parts of the world are voluntarily reducing their population, but here's the question. Why don't we have that conversation? Why don't we ask this generation about reducing consumption, about reducing carbon footprint, about having smaller families? Where's the place in society where that conversation can take place? Right now it's taking place among individuals making little decisions about personal consumption and family size. Where's the public policy arena for that discussion? So I want to open that up a little bit. It should be in higher education because that's why we do higher education. To have these conversations, to critique what society is doing. That's why it was established, particularly the public universities. To ask ourselves, what are we doing? And isn't there something else that we should be doing instead? Too much responsibility comes back to the individual, and it needs to be a collective responsibility. So think about that as you leave. Where's higher education on this?
We're not leaving yet, Pat. We got 15 minutes. But you're going to dare tell me how to live my life?
No, I'm going to explain the consequences of us together living a certain way, and you already get it. So I'm pretty optimistic that we will get it when education has done its job. And how do you explain the outrageous collection of behaviors in the current Congress? Is it a failure of higher education that we have so many climate deniers making laws right now? I think it is in part. Higher education gets an F on educating representatives and senators. How can we improve that? Can the science communities continue to stand by and not engage the public arena? Can we continue to talk as though our job is to write technical and journal articles and not get involved like Hansen did? Hansen got criticized in the colloquium a couple weeks ago. He should go back to his laboratory and do his science. We don't want him out there talking policy and education. I disagree. I think at some point we need to focus on our ability to not only articulate the technical problems, but to engage in the solutions, which are not always technical. They're moral. They're humanistic.
I'll come in as the optimist on this one. One of the observations that we talk about a lot with our energy fellows is the fact that Europe has a very high standard of living, Japan has a high standard of living, the United States has a high standard of living, but we use twice as much energy on a per capita basis. So right there is an example of some things that we can do that's going to reduce our energy use, reduce greenhouse gas emissions without making sacrifices. And I think sometimes approaching people with here's what you can do, whether it's recycle or switch out your light bulbs to have a positive impact in a positive way. People respond to that very well, and I talk to people all the time. They want to make a difference. I think 95% of the people are willing to do something. Now, I do think we have some national challenges, but we have a president who's willing to stick his neck out. We have interdisciplinary conversations going on all the time. We have some very sophisticated work going on at EPA, and one of the other things that the Energy Fellows have said is, you guys, and they look at me, I'm your age, Pat, you guys solve the women and the racial issue.
Nobody's my age.
and their energy challenges. I mean, I'm very optimistic, and I think technology plays a role, and I think faith plays a role, and all these things play a role. But I'm very impressed at the interest in business people of all kinds. Policymakers, our senators are very receptive. They want to hear the ideas, and they want to hear from the students, and they want students who are well-trained geologists, engineers, economists. I think there's all kinds of opportunities, and I don't believe in giving up until you've banged your head against the wall 50, 100 times, right? And then we can change. I don't know. I'd be curious to hear what you say.
Well, we actually had a sort of bring it home question that just is a general energy question, which is for Rhode Island, what is the leading energy concern? And what do you think of as the real alternatives for its resolution? So maybe I'll hand this right back to you to summarize.
Well, as I said, we've articulated some very high goals, 30% energy efficiency. We've got that goal in place. We have an economic model. We have a funding mechanism. It's still really hard to make it happen. So we're going to be slogging along right now. And when I say we, I mean people who own homes, people who own businesses, industry, policymakers. We're all going to have to work really hard to see that we do accomplish that. It's a cut. So it's instead of using 100 kilowatt hours per day, we'll all be using 70 on average. So that's a good thing. And then the second thing, as I said, is renewable energy, and we've identified 15% from offshore wind. So then, okay, what does that get to? 45%. That's still 55% that is going to be coming from gas or oil. And I'm not satisfied with that, but I don't see any easy answers on the horizon, and that's something that we have to really work on. And we are working on electric vehicles. We've got some great research going on right here at URI, cutting edge, top-notch research on lithium-ion batteries being done in the chemistry department. So there's some really exciting stuff. And I come from the Motor City, so the idea that we actually may transition away from gasoline-powered cars to some alternative is really exciting, and I think that's going to happen. Earlier today, there was a discussion of a biofuels mandate. Can we replace 15 to 20% of our oil that we use in our cars with biofuel made from either recycled waste oil or switchgrass or some kind of cellulosic product? So there's progress being made. We're slow. As I said, as good as our energy efficiency program is, we can't quite get our arms around how to structure the financial incentives for our renewable energy, and we're working on that really hard right now. And it's always, right now, you can't go to the State House in this poor state and say, we're going to charge the ratepayers another couple of cents on their energy bill, because the politicians aren't willing to support that. So we've got some challenges, but there's a good group of people working really hard to get around that. So I don't think it'll be nuclear. Add that.
I just make a quick plug in that context for systems thinking. It has a long tradition in ecology, but is also a big part of how people are thinking about things like manufacturing processes and energy production, with the idea being that if you understand all of the costs of a particular technological solution, rather than just the sort of myopic view of the particular problem it solves. If you're solving a problem but creating another problem, and you've ignored that, then you're not thinking about the whole system. And so that's a specific field of science that people interested in this kind of problem solving might be interested in.
Thanks. And I think there's some interest in the audience here about basically genetic modification of crops. So if we're looking at an era of increased atmospheric CO2, one thing to do is to think about genetically modified crops, maybe that could handle those levels as an opportunity for us. So what could be the global environmental effects of these kinds of crops, or do you foresee that they could be useful?
I'll try to be quick. Professor Craver had some of you folks do some readings, and this was one of the issues that was addressed. And one of the things that struck me is that Europe has been much more aggressive about first banning the use of genetically modified crops, but then saying, okay, what are the real risks and how can we manage those risks? And I was impressed with that. And I think in the United States, it's taking us longer to come to the table to make those kinds of hard decisions and analyze the trade-offs. I don't see us turning back on on that because URI is hiring more gene jockeys than anything else. I mean, that's kind of the future, one of the futures in science. So I don't think we're going to go backwards, but I think we need to think about, get the smart people at EPA thinking about the risks and how can we manage those risks. So that's my 2 cents.
If you can figure out who those people are, let me know. I've been struggling with this issue personally for a long time about genetically modified crops, and I don't have anything to offer in this situation because I have been unable to separate the scientific issues from sort of the moral issue and reverence for nature and all of that kind of stuff. So I don't have a pro or con opinion about it.
I've always got 2 cents. I have a book at home called The Rapture. It's another form of religion, not that religion, but the religion of believing that biotech will solve it all. The Green Revolution was extremely important in the 50s and 60s in providing new genetic strains that were essentially geared at responding to increased levels of irrigation and fertilization. In other words, to increase energy inputs. And we did really significant things with yields and durability. Biotech today continues that. In addition, it's looking at resistance to insects and diseases. I think all of that is very useful. But that's very energy intensive. It's another technology that you can put your faith in it, but be careful, because it's not the answer. You don't drive an acre of land harder because you've got harder working plants on it. You still have to carry the fertilizers, the nutrients, the water, the energy to make that thing work. It's not a panacea in my mind.
Anything to add, Becky?
I guess I was sort of thinking along those lines as Marion and Jason were speaking. The genetically modified crops are typically sort of planted by big agricultural industries, and they do so much more sort of ecological damage than the benefits that we maybe get from the increased crop yield or whatever in terms of nutrient loading and just energy and soil depletion. You know, soil could hold a lot of carbon, but it doesn't when it's sort of worked this way. And so this is, I guess, the disconnecting those 2 things is one of these system science problems that I can't get my head around.
I think I'm going to go ahead, and we have just a few minutes left, and wrap one of the last questions from the audience into a few summary comments. So the question that I'm still looking at here says really what current technological innovations could even have a real lasting positive impact in reducing CO2 emissions. And I was jotting down notes over the past hour and thinking a little bit about kind of the upshot or what we could take away from this time, this hour of our common existence here. And I actually jotted down some suggestions, pulling them straight out of a book called Smart Solutions to Climate Change, but Lomberg's book. Have you seen it? How many in the audience have actually encountered this text, Smart Solutions to Climate Change? It's fairly dense, but I'll share with you just the main themes out of the book. And the first is a focus on climate engineering. And some of you actually visited the Vedelson lecture some weeks back. There was a lot of talk about geoengineering of climate, especially things like solar radiation management, reflecting incoming solar radiation, or maybe generating a synthetic haze in the upper atmosphere that of reflective particles. Okay, there's actually a lot of experimentation being done right now. It scares you?
Well, it's just
kind of scares me too, but it is interesting. Another point is literally forestry carbon sequestration. We know from studying Earth system, trees do a great job of storing carbon, and so we should be supporting those initiatives sort of at every juncture. Black carbon mitigation. This is literally soot. Cut soot wherever you can, whether it's from diesel fuel, burning devices, or burning of organics. The next main theme is methane mitigation. Methane is sort of the bad sibling to CO2 when it comes to greenhouse gases. So keep an eye on methane cycles that are enhanced by our human uses of the earth. Being mindful of sort of paired market and policy-driven international cooperations. It's a global problem, so we're going to be needing global solutions. And then issues about being mindful of sort of the cutting edge of technology, forming climate policies in conjunction with technology development. So it's like, you know, you're always kind of using appropriate means to achieve whatever policy ends you have. And also a theme of technology transfer. So as long as we perceive that solar panels or other devices are out of our pocketbook range, you know, they really won't be useful to a wide span of the public. So a sense of making technology available to every person. But the theme that really, to my mind, is an umbrella theme that's covered every question asked here and also runs through this text is just about carbon dioxide mitigation. We have to have all of these themes running in parallel. So I'll close with just a comment coming from my own research interests. So I'm a geologist. I'm really interested in the rocks of the deep subsurface, our mantle. Wherever those are uplifted to Earth's surface, guess what? They're reacting with the CO2 in our atmosphere and mineralizing carbonate, locking it solid into mineral phases. And some would argue this is a really great, rich, permanent carbon sink. If anybody's interested, come to my office hours. Wednesdays, 1:30 p.m. Yeah, come by. But it's just an example of how I'm hoping that you're gonna come. You're gonna come too. But I put that out there as a detail that I hope is emblematic of a lot of individuals working in their own ways and means to try to combat this problem. And so sure, you know the drill, one person dealing with global warming. I jotted down from a dozen different websites: reduce, reuse, recycle, change a light, drive less, check your tires, use less hot water, all of that. Oh, and vote.
Vote, yeah, there you go.
Thank you for coming. And a special thank you to all of our panelists. Once again, Drs. Gold, Greer, Logan, and Robinson. And feel free to stick around if you have any last-minute questions. Thank you.